We learned how to apply entropy and the entropy change of the universe to predict spontaneity of processes. What we're going to do now is try to find a more convenient way to look at the spontaneity of reactions um, by invoking a thermodynamic quantity called Gibbs free energy. So here's our entropy change for the universe. And we call that, and here we can say that the delta S of our system plus the delta S of our surroundings. And remember, if we're dealing with a constant isothermal situation, so constant temperature and constant pressure, we can say that the delta S of the surroundings is going to be equal to negative delta H of our system divided by the temperature. So let me put our delta S back in here for the universe. Because what we're going to want to do now with this equation is we're going to multiply through by negative t. And what that's going to give us is negative t times delta S of the universe is equal to negative t delta S of our system plus the delta H of our system. This value right here then becomes the one that we're going to use to describe Gibbs free energy. So that negative T delta S will be referred to as Gibbs free energy, or rather delta G. So the usual form of this then that we'll see is delta G, so Gibbs free energy, is equal to delta H minus T delta S. And again, this is for a particular system, so we put that in there, or a reaction. And what this does is it allows us to kind of keep the surroundings out of the picture. So by using this equation, rather than trying to figure out the delta S of the universe and having to deal with the surroundings, we can focus strictly on just the system to determine whether it's going to behave spontaneously or not. So we've got Willard Gibbs here, who actually is an American mathematician, and he was the one who derived that relationship. One of the things that we'd want to look at then is, what can you say about the value of delta G for a spontaneous process? Well, remember we've got negative delta T, Gibbs free energy is equal to negative T times delta S. So if delta S of the universe, for that to be spontaneous, that value has to be positive. So the whole value of delta G, because there's a negative T in front of the delta S, for a spontaneous process, delta G must be less than 0. And so we can also look at what would be the other options. So delta G being equal to 0 would put us at equilibrium. And if delta G was greater than 0, that would mean that it would be spontaneous in the opposite direction. Now, one of the things we always want to remember that even though something's spontaneous in a particular direction, it doesn't mean we can't make the reaction go back the other way. We can always put work into something and force the reaction to go back the other way. And we'll see that when we get to the next chapter on electrochemistry. Batteries, they spontaneously will discharge and force electric current through something, so you can get useful energy out of a battery, but you can recharge batteries, so you can do work on that battery to force them to go back in the other direction. Here we have the Born-Haber cycle, the formation of ammonia, which is an equilibrium process. So we can look at Gibbs free energy for a system that's at equilibrium. Obviously, if we put in all reactants in this reaction, then at the beginning this is going to spontaneously go towards products. And again, that's what happens with all reactions, where things are going to go spontaneously downhill. Again, we can put work in and force them to go uphill, but they're going to spontaneously go downhill until you reach that point of equilibrium. And this can happen on either side. We could fill the reaction mixture with just the ammonia, in which case that would decompose into the nitrogen and hydrogen. And again, that change would be spontaneous. And it would happen until we reached equilibrium down there at the bottom. So you can see equilibrium situations, we can still apply Gibbs free energy, but obviously the concentration of your reactants and products is going to weigh in on the value of Gibbs free energy. So we're going to talk a little bit about that as we go through the chapter as well. Similar to enthalpy, entropy, we have a formula we can use to figure out the delta G for the reaction. Of course, we have a couple different ways. We can also use the formula here. If we know delta H of the reaction and delta S, we can use that to figure out delta G. We can also use our table of thermodynamic properties. So looking at the table, we can see that along with delta H values and entropy values, we also have delta G values. Some things to note here. Obviously, we're talking about standard state again. So again, we're talking about 25 degrees Celsius usually, or 298 Kelvin, 1.0 atmospheres. We want to remember that the standard state for for the elements has the same value of 0. So we've defined the free energy for the elements as having a 0 value in their most stable state at 25 degrees Celsius and 1 atmosphere. The other thing that we want to consider, so you can see that here for silver, for instance, for bismuth, iodine, potassium. The other thing you want to consider is that when we talk about solid, something that's a solid at 25 degrees Celsius and 1 atmosphere, to have 0 free energy, it has to be a pure solid. A liquid has to be a pure liquid. A gas has to be a pure gas at a pressure of 1 atmosphere. We also will work with solutions, so mixtures. The standard concentration of a mixture is 1 molar. All right, and that's where we look back at that last one where we had the hydrogen and the nitrogen combining to make ammonia. One of the things that made it spontaneous in each direction was the relative concentrations of things. So we will have to watch a little bit about that, but for the most part, we won't have to deal with the solution concentration very much. So back to our diagrams. One of the things that we'll do is, you'll learn how to apply our equation down here at the bottom to find out some different things. So you'll see the different types of problems we'll do in class. Probably do a couple, for homework with this. And then what we're going to do in the next section is take a look at how temperature will influence the value for Gibbs free energy.